So we have this system of linear equations here, and we want to solve it using Gaussian elimination. So I'm going to show you how to do that. Now Gaussian elimination is an algorithm that is very easy to program. So it makes it very useful to solve giant systems using computers. And this is the principal algorithm that computers use actually to solve systems of linear equations here. And the way it works is that you convert this system right here. So this is the system AX equals B, right? AX equals B. You convert that system into a new system um, called UX equals Y. And U is going to be an upper triangular matrix. So for U is going to look like, you know, 0, 0, 0, 0, 0, 0 in this case, and then there's going to be entries here, and I guess there's another one right there, right, like that. And this is nice because you can just so that times x equals b or y in this case, I guess. So that's nice because whatever these y values end up being, you can just you can solve very easily by back substitution by starting from this value and working your way up. And that's nice to program. So let's go through this algorithm here and how to do it. So this matrix here, we got to convert into an upper triangular form. And the way we're going to do that is we're going to find some multiples of each row, and we're going to subtract the previous row times that multiple from the current row. So I'll show you what I mean here. So we have that. Let's look at this row right here first. Let's look at this row right here first. So we see that this row needs to become zeros. So the way we can do that is we look at the multiple of this row, what it is times the first row. So we can do that by dividing um, the entries by the entries in the first row here. So the multiple 2, 1 is going to be the A21 entry over the A11. And we see that's minus 2 over 2 equals -1. And that makes sense, right? If you subtract, you used to take -2 minus -1 times 2, you get 0. So that's what we're trying to do, right? We're trying to get it to this form right here. So that's that multiple. Similarly, for the 4 down there, m 3, 2, multiple 3, 3, 1, rather, is a 3, 1 over a 1, 1. And that's 4 over 2 equals 2. And M41 similarly is going to be A41 over A11 equals -6 over 2 is -3. So what we do now is we take that matrix, that 2, 1, -1, -1, 3, -2, 0, 0, 0, 4, 1, -2, 6, -6, -1, 2, -3, and we put in the b's here because we have to change those for as well to get this. 13 minus 2, 24 minus 14. So what we do is we take this row here and we subtract off that multiple, -1 times row 1, corresponding entry in row 1. We do the same thing for this bottom one, minus the multiple 2 times row 1, and the multiple minus 3 times row 1. And what we see that that's going to, the top row is going to be the same, right? It's going to be 2, 1, negative 1, 3, 13. The bottom row, so minus 2 minus negative 1 times 2 is 0, which is that's the whole purpose of that. That's what we wanted. And then continuing on, we see that, 0 minus negative 1 times 1 is 1. 0 minus negative 1 times negative 1 is negative 1. And 0 minus negative 3 is negative 3. Or 0 minus negative 3 is 3, rather. So we see that's 3. And then doing the same thing, minus 2 minus 13 is going to be 11. And I'm not going to go say that that's a mouthful for each of these, but so I'm just going to go through here. I'm just subtracting 2 times the corresponding entry in row 1 from row 3 here, just like I just did for row 2. So that gives you 0, negative 1, 0, 0, and negative 2 right here. The 24 minus 2 times 13 is negative 2. And then the next row would be minus negative 3 times row 1, which is 0, 2, minus 1, 6, and 20, 25 there. Minus 14 minus negative 3 times 13 is 25. So that's after one iteration. All right, cool. We're getting close, right? Remember, the goal is to get to an upper triangular matrix like this one up here. So let's calculate our multiples for this one here. Notice that as we get further down this matrix, we get one less step we got to do work-wise. So we see that M32 multiple 32 equals the next diagonal entry, or rather, sorry, A32 over the next diagonal entry, A22, which is minus 1 over 1 is minus 1. Similarly, M42 equals A42 over A22 is 2 over 1 equals 2. So that means for this third row, we take minus negative 1 times row 2 and minus 2 times row 2. And that gives us, so notice this is fine. It's not going to affect this part right here, because when you subtract 0 minus 1 times 0, it's still going to be 0. So that's good. Yeah, first row is the same. 1 minus 1, 3, 13. Second row is the same. 0, 1 minus 1, 3, 11. The second row here, so we take 0 minus negative 1 times 0 is still 0. Minus 1 minus negative 1 times 1 is 0. 0 minus negative 1 times negative 1 is negative 1. And we see this is 3, this is 9. And then we do the same thing for the last row there. 0, I believe we get 0, 0, 1, 0, 3. And you can verify that if I think I copied something wrong. Did I copy something wrong? No. Or did I? Hold on. Nope. Nope, we're good. We're doing good here. Yeah, I mean, the one thing you got to make sure, this algorithm isn't terribly hard, but it is pretty easy to, mess up your 1 minus negative 1 times something. It's for me that I have to think about that a little bit. It's easy to mess that up, but there's so many times you got to do it, right? All right, so continuing, we got to find the last multiple, the multiple 4, 3. equals A43 over the next diagonal entry, which is going to be the, 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 the A33 equals 1 over negative 1 equals 1. So that means that this last row you take 1 or minus negative 1 times R3. That's going to give you 2, 1, negative 1, 3, 13, 0, 1, negative 1, 3, 11, 0, 0, minus 1, 3, 9, 0, 0, 0, 3, 12. All right. Yeah, no, this is great too because we've essentially we've done it. You know, we've converted this to an upper triangular system. So this is our U matrix and this is our Y vector replacing A and B respectively. So we can solve this quite easily by back substitution. So this x4 we can get from this row right there, the fourth row. So x4 is just going to be 12 over 3 equals 4. X3 we get from that third row. So that's going to be 9 minus 3 times 4, right? 3 times x4, 3 times 4 over negative 1, which is going to give us minus 3 over minus 1 is 3. Good so far. X2 is equal to 11 minus 3 times 4 minus negative 1 times 3, our x3 value, over 1. And that's going to be 11 minus 3 times 4, yeah, over that, so that's 2. And then the last step here, can't really see what I'm doing, I guess I can still right there. X1 equals 13 minus 3 times 4 minus negative 1 times 3. By the way, these negative 1s and 3s, that's just a coincidence that these are the same number. It doesn't necessarily have to be. Negative 1 times 3 minus 1 times 2 over 2. I think when you evaluate that, you get 1. So our x vector solution is going to be the vector 1, 2, 3, 4. And we've just solved it using Gaussian elimination. And one thing to note is there's an interesting property with this method is we solved it only using type 1 row operations. We didn't swap any rows basically. We didn't have to. And you can do that when the each leading principal submatrix, the determinant of that is 0. So let me write in a different color here. Do a fun one. How about that? So when we look at the determinant of this matrix, determinant of this matrix, the determinant of this matrix, and the determinant of the whole matrix there. If those are all not 0, if all those matrices are non-singular, then we can perform this Gaussian elimination algorithm only using type 1 row operations, meaning we won't have to swap any rows. So that's an interesting property there.